So in this part of the video, we will continue from where we left in the last part, and we will cover some more type of adders and subtractors in this part. So in the last part we have discussed about half adder, half subtractor, full adder and full subtractor, and that too with the basic gates. We've implemented them with the help of basic gates and NAND and NOR gates, and also the derived gates. So continuing from there itself, let us see now the circuit, a single circuit in which we can perform not only addition but also the subtraction. So this circuit is basically, we will implement first for 1 bit operation, and then later on we will see it for multiple bits as well. So let's suppose we want to make a circuit which can perform not only addition, not only a single operation, but the two operations, okay, the two important operations, the two important basic operations I should say. So it should perform addition operation as well as the subtraction operation. So we will do this with the help of our, let's say, a full adder. Okay, a full adder. We want a full adder which can perform not only addition but the subtraction. So how we will do this? To do this, we will include in the on the input side, we will include one more variable. Okay, and that variable we will call it as mod control. Okay, so it is mod control which will help us to get the circuit which can perform not only addition but as well as the subtraction. So what we do in this case is, let's say we have 3 bits. So M is one of the bit which can be our mod control, or it can be our, you can call it the input carry. Okay, and the other 2 bits are A0 and B0. Now for this particular, if these are the inputs and we want the circuit to perform not only means both the sum and difference operation, then how the circuit will look like. So let us see that. And it will not only generate the sum and the difference term, but it will also generate the carry or the borrow term. Okay, so see this, we'll see this, how we'll do this. So let's say these are our 3 inputs. So we say that whenever input this mod control, whenever this the circuit output we want is something like this particular input combination should be able to control the operation. Okay, so it is basically a full adder, but we are using a logic of half adder. Okay, so what we are saying is that when this M input is 0, the operation should be, the 2 bits should be added up. Okay, so the operation should be when these 2 are like this. So your addition operation will be performed on A and B. So you can see that in this case your addition operation, you can see, okay, so carry is generated and the sum bit is 0. Whereas when this bit M or C in is 1, in that case the difference operation has been performed by the circuit. So you see this again same thing. So you see we have like added up the truth table of the half adder and a half subtractor. So you see this is the operation when the number which you need to subtract is greater than the number from which you have to subtract. Okay, so this is 1 minus 1, 0 minus 1 will give you difference bit as 1, whereas the borrow or the carry bit also is 1. You can call it carry oblique borrow. Similarly, this is like same, and 1 minus 1 is 0. So this M you understand it now. So based on this operation, if you write its truth table, okay, so the truth table for S and S oblique D and C1, so then you can find that when M is 0, so that is what I have told you, so addition operation is performed when M is equal to 0. So in this case, if you will draw its truth table and write the operation, so then your I should say it is B, okay, B, or you can write it as C1, okay, B or C1. So okay, sorry, b is, let's say, intermediate, no, it's not borrow, it's intermediate variable, which is your b0 plus m, okay, b0 XOR m, okay. So you can see that if b0, if b is like intermediate variable, some intermediate variable is there, so this should give you this input variable plus XOR of m, okay. So you can see this by just looking into the operation of this m and b0, okay. So you can see that from the same thing we'll get the circuit as well. So you see, what I mean to say by this is, like when you perform the addition operation, what happens? See, I have told you already that this is our, with this when m is equal to 0, what we are trying to do is, this is our half adder, and for this when m is equal to 1, this is half subtractor. This is the truth table, this is the combination of the truth table of half adder and the subtractor and a half subtractor. So basically what I want is this, if you understand this particular operation, okay, which I have written here, then we will easily able to get the circuit for it. So what we want is, when m is equal to 0, we want an intermediate output, okay, which should remain like the input of the other input of the half adder. Because you see, if you have, like, suppose if you want to implement an half adder, then when this m is equal to 0, it should work as an half adder. So this b should be equal to b, okay. So the other variable, the intermediate variable, should be equal to b0, okay. So in that case, our intermediate input, mod control, should be equal to 0. So what we want is, if we suppose XOR it, so you will find it that b is equal to b0 XOR 0. So if you write in this one of the output variable as, let's say, intermediate output as b, and write the truth table for it, so you will see that b should be equal to b0 plus b0 XOR 0. Why? Because our b should be equal to b0 in this case, okay, intermediate output, because we want the circuit which should perform which should perform both the operation, addition as well as subtraction. So we have to manipulate one of these inputs rather than both the inputs. So we will keep one of the input as it is, a, whereas we will manipulate the other input. Let's say we are manipulating here the b input, okay. So then that is why I have written this expression. You can do the same for a as well, okay. So now you see, if you XOR them, so then your b will be equal to b0, okay. And if b is equal to b0, then you can easily see that b0, and as you can see that the same term, the same input we are calling Cin. So your Cin is also equal to 0 in this case, okay. So half adder Cin is equal to 0, okay. So this is what I was saying you, that this is working as an half adder. So this operation is like a plus b, okay. So this, when m is equal to 0, see, a plus b's operation is performed. Now you see the other thing, when m is equal to 1, okay, when m is equal to 1, in this case what is happening, we have to, again, you just recall that if suppose for this particular case we want the circuit to work as an half subtractor. So there is a slight difference between a half adder and a half subtractor. In half subtractor, you just add an inverter in one of the input, okay. So that is what the difference is. So what we will do is, we will again here generate an intermediate in output, which will become the bar of the input, okay, bar of this b0. So our output, intermediate output, should be equal to the complement of b0. That is what we want. So how we will do this? We will do this by performing again the XOR operation. If you write the intermediate, this variable b, intermediate, you write by yourself, okay. So you'll see that you'll observe this can be good exercise for you to understand the thing as well. So you put an intermediate variable in between, let's say here b, and then write the truth table for this, the entries for this, and you will see that b is equal to, then b0 is equal to XOR, where this b is equal to b0 XOR m, okay. And when m is equal to 1, so you will see that it is equal to, b is equal to b complement, okay. b0 XOR 1 is always equal to this b complement, because you see b0 can be either 0 or 1. So if it is 0, your output will be 1. 0 XOR 1 is 1. Whereas if it is 1, then 1 XOR 1 is 0. So you can see that it is by doing XOR with 1, okay, by XORing it with 1, you are getting B complement. Okay, whereas if you XOR B0 with 0, then you will see it will always give you B0. Okay. Okay. So this is B complement, and then Cin is also equal to 1 in this case. So you see, if Cin is also equal to 1 in this case, so you get that B gets the complement. Okay, B gets complemented, and this plus 1 as Cin is also equal to 1. Okay, so in this case you will see that the operation is the operation which is performed by this half subtractor is the operation by the help of 2's complement method. Okay, as Cin is also 1 equal to in this case. So you will see that the circuit will become something like a subtractor. So if you implement this particular logic, whatever is written here, in the form of the hardware logic circuit, then you can see that A0 will remain as it is, whereas in B0 there will be an XOR gate. Okay, B0 will use an XOR gate, and the inputs of the XOR will be M and B0, and the output will be that intermediate output. Okay, B, and you will see that M will always be equal to Cin. So that is why we have written M is equal to Cin. So M is equal to Cin, and then you can see that your output will be at this terminal, it can be sum or difference, whereas the carry output will be generated from this terminal. Okay, so this is how you can perform with the help of same circuit. We can do not only the addition but the subtraction also. So moving on to the next topic after this, now we will see that how to perform the in the last few slides we saw a single bit adder and subtraction operation. Now we will see a multiple bit adder. So first we will see a parallel adder. So the difference between the single adder and a parallel adder, and this particular single adder only we are going to use multiple times to make a parallel adder, okay, or a multi-bit parallel adder. So I was telling about the parallel adder. So when you say it is a parallel adder, so it means that all the sum bits are generated simultaneously. Okay, so the operation is performed simultaneously. So that is why it is called parallel adder. Now you will see that we have used a single full adder multiple times, as many times as we have the number of bits. So here we have 4 bits, so we have used the full adder 4 times. Okay, now A and B are 2 numbers, each of which is a 4-bit word. Okay, the bit length is 4 bits of each of this word. So what we do, starting from the LSB, so A1 is our LSB and A4 is our MSB. Similarly, B1 is our LSB and B4 is our MSB. And we are also getting this some carry input. Okay, so as soon as the carry input is there, now what happens is, for this particular circuit we apply all the inputs simultaneously, but the output although is generated simultaneously, but it is not correct. Why it is not correct? Because the carry output is propagating, is rippling actually. Okay, this is what is called as this carry, this type of parallel adder is also called the ripple carry adder. Why? The reason is because this carry is propagating, is rippling from one full adder to the another full adder. So the point is, until and unless this carry, the first full adder does not generate this carry, okay, the sum bit generated by this full adder will not be correct. So this correct carry should come as once this carry is generated, then only this full adder will generate its sum output and the corresponding carry output. And the this carry output generated by this sum and the sum bit will be correct only if this C3 is available. So you can see that this type of parallel adder can be useful for implementing the operation for multiple the word length, the words which the codes or words which are multiple bits, like say in this case 4-bit. So it can be used to perform multi-bit operations. So that is the advantage. But the other disadvantage, one of the biggest disadvantages, that the time required, okay, to generate this carry or to ripple this carry is like this final carry will be generated once all these carries are generated. So you can see that this is the advantage, the propagation delay. So the time required by this circuit to generate the correct carry and the correct sum bits, okay, will depend upon the propagation delay, the time delay after which the circuit will generate its carry output, okay, first carry output. Each of the circuit will generate its carry output. So the total propagation delay at the output is the accumulative propagation delay of all these blocks, of all these full adders. So this is what the circuit has some advantage, but it also gives some disadvantage also. So you can see that this is the general thing by which you can implement a parallel adder. Okay. Now let's see a circuit which can perform the subtraction, 4-bit parallel subtraction. So 4-bit parallel subtraction, again the same problem will be there in this type of circuit, because the this carry or the borrow is propagating here in this case, and we are using the full adder circuit. Okay, same. But you know that the difference between this half full adder and a carry, this full subtractor, is that you just put a inverter here. So we have just used an inverter here. Otherwise the circuit is same as the previous circuit. But if you use this inverter in one of the inputs, then it will become a subtractor. Okay, parallel subtractor. So this was about the parallel subtractor, and it generates all the sum output and the carry output. Okay. Now let's see the same thing which we have seen in our the very first slide of this particular part, that how to implement a adder and subtractor in a single circuit. So in this case, for this 4-bit circuit, if you want to implement the circuit, the single circuit in which the addition and subtraction operation both are performed, then the logic will be same. We will use an inverter, okay, sorry, an XOR gate here. Okay, the XOR gate, each of the inputs of this XOR gate is connected to mod control, whereas the other inputs are as it was in case of a single bit adder and subtractor circuit, whereas the other circuit where the other input is also same. Okay, the other inputs of the XOR gate are also same. So if you understand that particular logic which we have discussed it for 1-bit adder and subtractor circuit, then it will be very easy for you to understand the 4-bit adder operation, adder subtraction circuit as well. Okay, so this is what the circuit is. So here in the digital electronics, this is what the good thing is, that you just have to replicate the circuit multiple times if you want the circuit to perform multi-bit operations. Okay, so this is the good thing for digital circuits. So this is how we do it. Okay, so in case of any doubt in this particular 3 type of adder subtractors, we can discuss it, but they are self-explanatory and doesn't need any explanation, because if you understand the very first circuit, then things are very easy. Now let us see the more important adder, which is called the look ahead carry adder. So this look ahead carry adder, the first question is why we need to make a look ahead carry adder. So this is the look ahead carry adder is basically adder which is like invented by professor mathematician. His name is, I just can't recall his name, but probably his name is Charles Babbage. Okay, so in somewhere in 1870 or somewhere, okay, 70, I don't know exact year, but somewhere, okay, 1900, around 1900, he invented this what is called as look ahead carry adder. Okay, Professor Charles Babbage, and he was from England. So he invented this. So what was the logic to invent this? So he invented it to overcome the shortcomings of your parallel adder. So the parallel adder have the shortcoming of this particular which we have discussed, that the ripple carry is there and it takes more time to calculate the exact sum. Okay, and until and unless the fifth carry output is not, the final carry output is not generated. So the propagation delay is more in case of parallel adders. So to reduce this particular thing, or to overcome this deficiency of parallel adders, okay, this particular thing of parallel adders, he proposed this this look ahead carry adder circuit. So how we'll do this? Okay, we'll see this. So the logic, first we'll see the logic, and then we will see that how it is used to perform the look ahead carry adder generation. So first we will make a circuit which will generate this carry, okay, simultaneously for all the bits, and then by the help of that we will implement look ahead carry adder. So it is also called carry look ahead addition process. So in this, what we do is, this is our usual process. So there are three inputs. So what we are doing is, we will implement it for a full adder. So if we are able to implement it for full adder, and if we replicate it multiple times, then we can make any type of bit length adder or subtractor circuit. Okay, so let's start with our full adder. So if I just consider a full adder excuse me. So what I am doing here is, we have three inputs, and these three inputs are as usual as they are for our full adder. So these are our inputs A, B and Ci. And for this circuit, see, our basic aim is to manipulate our carry, to generate the carry simultaneously. We will not do anything with the sum bit, the sum output where the sum is generated, but we will do something with the carry. Okay, so that is why I have not shown the sum output here. Okay, there will be two outputs, sum and carry output. So carry output, which is written here as Ci plus 1, is shown here. So if you make Ci as your input carry, so then Ci plus 1 will be your carry output. Okay, sum output is not shown here, but there will be some sum output. That sum output we will see later on. Okay, our basic aim is this look ahead carry adder generator. This carry adder circuit is basically a circuit which manipulates your carry generation process. So we'll see that. So we'll with this all process, what we are going to do is, we are going to generate a circuit which, a carry generator circuit. We will design a carry generator circuit. Okay, so you see, this is our carry output. So by just observation, if you will see, then you can see that in these two cases, okay, no carry is generated. Okay, you see, not only these two cases but three cases, no carry is generated. Okay, when this one of the input is, when there is only one input is 1, so in those cases the carry output is not generated. Whereas in the other cases where this particular happens, where this for these three cases, what you can see is, your carry doesn't propagate. What does it mean? It means that whatever is your input carry, the output carry is also same. If the input carry is 1 here, in this case the output carry is also 1. Okay, so you can see this. So you say that the carry is not propagating, the carry is same for these cases, for these three cases. Whereas for these two remaining cases, the carry has to be generated. Okay, so you see, first of all, you have reduced it in some way by just observing. So in this case, in these two cases, when for these two cases, when A, B and C input is this combination 1, 1, 0, and when all the inputs are 1, 1, 1. So for these two cases only you have to generate carry. Okay, so considering this particular thing, so you just keep this in mind. So this is the truth table for your circuit. Okay, now before moving on to this particular how to use it, let's see that we have studied this half adder earlier, and this half adder, if suppose we write the sum and the carry bit, carry output as, let's say we denote it by some other outputs, which are in this case Pi and Gi. So you know that this is our half adder look, how a half adder will look like. So the sum output is nothing same as A XOR B. So we have denoted it if we denote it with something like Pi, okay, so we can denote it with Pi, no problem. Similarly, we can denote the carry output if we denote the carry output with Gi. So our Gi will become A cross A dot B and our Pi will become A XOR B. Okay. Now considering this truth table and this basic fundamentals, if we like suppose what we do is, so in general we have written it in the previous slide. Now considering this previous truth table, if we see that how our carry input can be written for a full adder, okay, for a ith stage, is for a general stage I should say, okay, nth stage or ith stage. So the carry input circuit is something like, so I have shown here the circuit with the help of gates and a general block diagram also. So whatever way you want to understand it, you can understand it anyways, but these things are same. So this is our one of the half adder, so this half adder is this, whereas the other half adder is this, so this is shown here, whereas this is one OR gate, so the OR gate is here. So the two circuits are same, okay. This circuits we have studied earlier also. So the output of this particular XOR gate, I have told that this is Pi, okay, and this output is A XOR B, whereas the output of this AND gate, I told you that we can denote it by Gi also. So we have denoted by Gi and it becomes A dot B. Now if we consider this as our full adder, which is nothing but a combination of two half adders and a OR gate, so the output of this XOR gate will be our A XOR B XOR Ci. So no change, and we won't manipulate it. So let it be as it is. But now the thing is here. So you see here the output, you can write it, the output of this AND gate, you can write it as A XOR B dot Ci, right? So you see this is A XOR, this is our what, A XOR B, and this is the other input is Ci. So this is our other input Ci. So this is coming here, okay. So you can see this. So this we have written as Pi. So the output here will become, let's say, Pi XOR Pi dot Ci, right? And this is our Ci plus 1th input, a Ci plus 1th carry output. So if this you denote I as 0, so your I plus 1 will be 1, right? If you make it as 1, I is equal to 1, then Ci plus 1 will be equal to 2. So if input is 1, the output will be 2. If input is 0, output will be 1. So, okay, so consider this. So now in general sense, if I want to write, so I can write it as Pi Ci plus Gi, right? So this is what we are getting it. So Pi Ci I am getting. So I have written it as what? Because this is XOR. So XOR of Pi Ci and Gi. So this is written as Pi Ci plus Gi. So this is the general ith stage parallel adder. Okay. Now you can consider this, and it is same. So I won't explain it again, but you can understand it if you want to understand it with the help of block diagram. You can understand it here with this circuit as well. Now considering your truth table, which we have seen earlier, okay, and this particular thing, if you see, so the general expression if you write, so then the general expression which I have written earlier, which is Ci plus 1, so I have copied that expression here. So Ci plus 1 will become your Pi Ci plus Gi, okay. Now your Gi can be this Ai dot Bi, and Pi is equal to Ai XOR Bi. This I can take any value from 0 to n. N is the number of bits for which you want the circuit. So if you want the circuit for 4 bits, so n will be 4. If you want the circuit for 6 bits, the circuit will be, this n will become 6. So we'll consider it for 4, okay, for n is equal to 4. We'll analyze the circuit for n is equal to 4. So you see, if considering this, let's say, if I substitute I is equal to 0, so then this expression Ci plus 1 is equal to Pi dot Ci plus Gi will become something like this, P0 C0 plus G0, okay, for I is equal to 0. Similarly, for I is equal to 2, it will become this, I3 C3 C4 for I is equal to 3 and 4, they will become like this, the expression will become like this, right? Now if we substitute the values, because you see in this expression what I am getting is G0 plus P0 C0. Okay, now this P0 and C0 are nothing. C0 is our input carry. Okay, because if I substitute I is equal to 0 in the previous case, so it will become C0. Okay, so that is what it is. And P0, if I substitute in this case, whatever I am getting, I is equal to 0 as I have told you. So the output of the very first half adder, if I is equal to 0, then it will become P0. So this is our P0, this is our G0. Okay, so you see, this is what we are getting. So we have written the expression like this. So this is our P0 Z0, but in this expression you will see that C2 is equal to G1. So G1 plus P1 C1. C1 is you are getting from this expression. Okay, so C1 is from this, whereas P1 is after your first full adder. Okay, so you can consider that C1, C2, C3 values you are substituting from here. So C1 you substitute in this equation, you substitute from here. C2 in this equation you substitute from here. C3 from this. So you see, our basic aim was, as I have already told you, that to manipulate our carry. So that is why we are writing this whole expression in terms of our carry only. Okay, so you see, if we substitute these values for C1 and C2 and so on, we can find that our C1 will be no change, because it is this P0 and C0 are all are independent, so no problem. But the other C2 will be again will be the function of P0, P1 and C0. Okay, so you can write it. Similarly, you can write C3 in terms of the this P0, P1 and other variables. Okay, so you can rewrite the expressions for C1, C2, C3 by just substituting the expressions of C1, C2 and C3. Okay, from here. So you can see that your expressions become something like this. Now once you get this, this is what you wanted. Okay, so you have manipulated C1, C2, C3, C4. Now you are not generating the carry output of first full adder and substituting it, making it the input of the second full adder, but you have written the equation which will be helpful to realize a circuit which can generate all the carry outputs simultaneously. This carry outputs can be generated simultaneously if you can implement this type of circuit, okay, with these combinations. So you can see that this is nothing but an expression in the form of sum of product terms. Okay, so to implement this circuit, to implement this particular circuit, we can use and OR gates. So you see, in this expression, if you see, C1 is equal to G0 plus P0 C0. So C1, to implement C1 is no problem. So C1 is the output of our first full adder. Okay, that I have not shown here, but you can write it directly as well. But C2, if you will see, then it will be G1 plus G0 P1 plus C0 P0. So you see, C2. So C1, I am considering that C1 is already generated after your first full adder. Okay, although it can be written like that as well. Okay, so you have the C1 here. So C1 G1 P1. So you have made a circuit which is an AND gate which takes P1 G1 as that its input, and then they are ORed together to generate a C2. Okay, similarly P2 and G2 are at this particularly for to realize this expression for C3. So if you realize this expression for C3, then you can see that it is G1 G2 G1 P2, sorry. So you can see that G1 and this is our G1 and P2. So to this particular AND gate we are giving G1 and P2. Okay, whereas to this AND gate we are giving what? We are giving see this is becoming, this AND gate is our C1, then this input is our P1 and this input is our P2. So it is C1 P1 P2. So you can see that. Okay, for C3 you will see that the expression is, if I made it correctly or if I made any mistake, I have to check it. Okay, so you see, this is what we are getting. So this is the circuit for our, what I was telling you is C3. So C3 is this term. So there was a confusion in this. So you just check it. Okay, so C3 is this P1 and P2, where is P2? So this is C1 and this is P1 and this is P2. Okay, so this is right, this is not wrong. So why C1? Because you see, if in this particular equation C3, the equation of C3, if you check, if you take from this last two terms P1 and P2 common, so whatever is remaining, then that will become as C1. So if you take from these two terms P1 and P2 common, the remaining things will be G0 plus C0 P0, and that is equal to C1. So that is why, rather than taking all of them, we have just taken C1 because C1 is available. Okay, so C1 is this. So that is why C1. Okay, so now you see this C1 is there. So C1 is this. So this is this terms, this particular gate, it generates that term which I have explained you, and the OR of this gives you C3. Similarly, the expression for 4 can be realized with the help of this 3 AND gates. You may see that, you can see that the AND gates are all the AND gates are not of the same inputs. So the number of inputs to each of these AND gate are different, and similarly the number of inputs to these OR gates are also different. But if you just consider this, then this circuit which you can see here is called as your carry look ahead generator, and this is the circuit which is used to reduce the propagation delay, or which is used to overcome the particular deficiency of your parallel adder, okay, ripple carry adder. So this circuit overcomes your ripple carry adder problem. Okay, and this is the circuit which was invented by Charles Babbage, as I have told you. And this is also available in the form of available as a 16-pin IC, okay, which is like 74182. So this people remember, and this is 74182 is nothing but, if suppose in some Viva or somewhere it is asked that what is the typical IC number for a carry look ahead generator, then you can very easily say that it is 74182. Okay, now this particular circuit I have taken from the website, one of the website. So it is the electricaltechnology.org. You can see in its watermark also, because this circuit was a little difficult to draw, so I found this particular circuit good, and I am thankful to this electricaltechnology.org to include this particular circuit. In the next few parts also I will show you some circuits which I have taken from some websites. Okay, so some of you can help me out to redraw the circuits if you can. So as an assignment, I'll give you some of the circuits to draw. Okay, so you see this look ahead carry generator, if you can see that how it is used to perform this look ahead carry operation. So you see this IC which we have just now seen, which is our 74182 IC sort of. So this 74182 IC, okay, it is again sort of this particular, okay, not this IC, but this type of circuit is included in another look ahead carry adder. Okay, so that look ahead carry adder is how it implements the circuit. So this half adder, so this is the half adder which we have seen earlier in the very first slide of this introduction of this look ahead carry adder. So you can see that this particular block is having the first half adder. So that half adder is generating your P0 G0, P1 G1, P2 G2 and P3 G3. Okay, so here in this case the terminologies, the output variables are a little different, but no need to get confused with that. Okay, so the inputs are written as C0, A0, B0 and like this. So these are our inputs, so this is our outputs are generated. Now once these outputs are generated, then you can take you can feed this to your look ahead carry, this carry look ahead block, and then those outputs, okay, so this C1, C2, C3, C4 are directly generated from this look ahead carry adder. Okay, so this particularly carry look ahead block, and then this are fed to this particular XOR gate. So this XOR gate is the XOR gate of the other output, the sum output. So where the terminal from where we were generating in our full adder, the terminal from where we were generating the sum output. So this is that XOR gate. So that XOR gate is used here as an adder. So now you can see all the sum bits are generated simultaneously, and this carry out is also generated simultaneously, which is your C4. Okay, so you can see that this is how you overcome the deficiency of your parallel adder. Now this circuit you can see in this form also, and the IC is I have shown it separately because if there is like difficulty in understanding that circuit because of the watermark, you can understand it with the help of this. Okay, and the other point you may have that the number of terminals which you can see here are not 16 as it was told here. The number of pins, why they are not matching is the reason because if you will consider an IC, so it will not only have this pins, but it will also have ground and VCC pins. So if you will include all those pins, other useful pins as well, so then you will get easily that it is a 16 pin IC. Okay, so you may not find them all the terminals here in the this particular circuit. Okay, so this is your look ahead carry adder, and this is also used in an IC which is nothing but a parallel adder. Okay, a 4-bit parallel adder. So in this a 4-bit parallel adder, what we do, we take two numbers which I have already shown you in the last slide. So you see there are two numbers of each of 4-bit and we have added them together. So that IC is your 74283 IC. Okay, 74LS83. So what is this terminology? We will study in our next unit probably. Okay. So this is how your parallel IC parallel adder looks like, which this parallel adder IC 74LS283 or 74283 uses carry look ahead operation. Okay, so look ahead carry generator is inside this full adder, and this is different than your normal parallel adder, and there is no propagation delay in this case, and the operation will be little fast by using this IC. So what are the advantages and disadvantages of this look ahead carry adder? So the advantages, as I have already told you, that the propagation delay is reduced and it provides the addition. It makes the addition faster. The addition operation will become faster. Okay, but the disadvantages, as you can see easily, that the circuit becomes complicated. Okay, and the number of variables increase. The other disadvantage is that if you have to make an extra IC, then the things will be not that much costly, but if you consider the cost, then automatically the cost will be slightly increased. So the circuit is little costlier. Okay, so these are the two advantages and disadvantages of look ahead carry adder. Now let's move on to, okay, this is not useful to you, so we will not understand it because this will involve a lot of mathematics, so you don't know that, so I'm not going to discuss that with you. Then we will move on to the BCD adder. So okay, this BCD adder I'll continue in the next slide because in the next part, because this part is getting little longer. Thank you for listening this part. We'll complete the BCD adder in the next part. Thank you for listening.